All right, let's talk about electrical imaging of groundwater surface water exchange due to logjams and associated geomorphological complexities. This exchange can be called hyporheic exchange flow, which is exchange between the stream and the hyporheic zone. The hyporheic zone being a shallow groundwater zone that is a really great natural bioreactor that can improve stream water quality and is important in stream renaturalization and ecological function. Logjams in the schematic down here affect the hyporheic zone and thus the exchange between the stream and this hyporheic zone by creating backwaters that can do basically two things. They increase material deposition behind the logjam, increasing the size of the hyporheic zone, and can increase hydrologic pressure gradients across the logjam area at about the meter scale. So these gradients can force water deeper into the stream subsurface, increasing residence times and mass exchange, and increasing the size of the hyporheic zone. Logjams also, although not illustrated in this schematic, tend to increase the complexity of stream channels by helping the formation of multiple channels and stream channel islands. So this schematic is of one of our reaches of the 4 we did in the Little Beaver Creek in northern Colorado to observe how logjams affect the hyporheic exchange flow. So from left to right here is stream flow, our logjams in the center. We have 2 observation transects, both comprised of co-located electrical conductivity that is in stream and a line of electrodes done to use electrical resistivity that studies the subsurface. So to kind of poke the bear and get a signal from our system, we injected a conductive tracer of sodium chloride into the stream to observe how it exchanges with the hyporheic zone and the stream. So this tailing here in the tracer is mostly what we're looking at, and it is a proxy for residence times and mass exchange between the hyporheic zone and the stream. So we quantify this tailing with a measurement called skew, and here we have box plots of each of our reaches, upper and lower lines, and the red line here is the median value comprised of this distribution across several discharges of the tracer tests we did. So overall skew increases with increases in complexity being delineated by our reach numbers here, reach 1 being single channel no logjam, reach 4 multiple channels, multiple logjams, and the other reaches being in between those. So skew increases, and this suggests that complexity increases hyporheic exchange flow in streams. We were also able to use the electrode line to determine or guess at the distribution of tracer in the subsurface using inverse modeling. So in this right here, this is a cross section of our reach 4 upper transect, and this is our main channel. This is an ephemeral wetland right here and a side channel. And the bluer it is, the more estimated tracer there is within that. So we see tracer entering across this whole entire reach. And what's kind of important to take away from this is that this provides evidence that the more surface area is more exchange for the hyporheic as compared to a single channel. And then also the side channels in the wetlands actually keep similar retention at lake time to the main channel, although they have less discharge, thus helping increase residence times in the hyporheic. So I know that was pretty quick and short, but if you have any questions, want to follow up, there's a lot of other cool stuff going on with this project, please feel free to email me. All right, thanks for watching.